I think I will start here, and then people will join us as they come in. So welcome everybody to DHI's webinar series, Diving into Water Innovations. And today I will be the presenter. I'm Jakob Thornfeldt Sørensen. I'm a product innovation portfolio manager here at DHI and a researcher. And in the work I'm presenting today, I've worked closely with Stefan Kistner, who's a co-presenter here and will be there to answer questions as well. He's done the hard work, to be honest, and I will be presenting how that is integrated into some of the work we're doing. The topic that we have today is on high-resolution ensemble wave predictions for all, and how we have orchestrated that inside our forecast service called DHI BlueCast, or how we are planning to do that. And let's jump right into it. So the topics we will be covering today is first a little bit about what is a good forecast. We'll have a easy ramp up, and then we will dig more into how to produce machine learning downscaled ensemble predictions. And after going through that, that will be the majority of the presentation today. We will be presenting some results fresh from the oven, or that was from yesterday. We have older ones, but why not update? And then we will have a little look on future perspectives. So the setting here is mid-ocean forecasting, so weather and waves, and mainly offshore. And we will be focusing on waves for offshore operations. And as you see here in the right, it could be for offshore wind farms or other, could also be transport, other sectors operating offshore that are in need of knowing the conditions in the future. So what is a good forecast? Well, let's start with a quote from a fellow countryman. Prediction is very difficult, especially if it's about the future, said Niels Bohr when he had to explain what dangers you had going beyond the data you have had when trying to extrapolate what you think is the truth. And if you think that today is the truth, then trying to predict tomorrow, you would say, okay, the weather tomorrow would be like the weather today. It's actually not a poor forecast. I think it's, if I remember correctly, something like 70% of the time it's true, more or less so. So that's called naive forecasting or persistence. And I'm mentioning this because if we start doing advanced methods, we should make sure that the baseline, what we contribute with, is better than naive forecasting. It's not knowing anything. There's another very achievable, at least when you are in the world where we have been before, achievable comparison, which is climatology. So if you later this month, I think I'll be fortunate enough to have a business trip to Japan, then it's good to look in the climatology to try and have an assessment of what will the weather be like. Of course, I can look at a seasonal forecast, but more or less it will be the quality of a climatology also a bit improved. So then I can look at a climatology, or what are conditions like? Is it hot or cold? That is also a prediction that we should be better to do better than. But of course, this is not what we see in the news every day, or what we provide to people operating at sea. You need much more accurate data, and there you come into mid-ocean model forecasts. So we have big meteorological centers, as we all know well, where forecasts are produced. And then when you go into areas that are specific to something you have, some valuable assets you have, or some operations you have, then you can downscale that and gain accuracy in a specific area. And you will then know, here we show an example of a significant wave height from our DHI BlueCast service. and how the prediction looks for that significant wave height, a maximum wave height, and also here we have a mean wave period prediction over the coming 4 days. I think I got that yesterday. So this is something that we can also provide, but this of course is a more costly thing than looking in a climatology or saying the weather is the same today as tomorrow. So why do we do this? Persistence, if you look, what you have here is a forecast in days in advance. So it's kind of a forecast horizon on the x-axis and some measure of error on the y-axis. And it will of course deteriorate very fast. You will get worse forecast after some days, depending on where you are in the world. This is a schematic illustration. Maybe climatology is or not maybe, but then climatology will actually start being a better guess than looking at the weather, say, 7 days ago. Then you have a good guess from that. And what we then provide with the mid-ocean forecast is to model things that are based on observations of where are we now and the chaotic nature of the atmosphere and how that is transferred into waves and flow and water level, is then giving a worse and worse also prediction as you go along, but you keep a good skill for a longer time. And this is what we're trying to achieve in mid-ocean forecasting. Now, if you notice, there's still a gap from here to zero. And this is a statistical kind of assessment. You could look at, okay, how was the forecast the last year? And you can come up with a curve like this and say, how good will I in average be? But this actually varies quite a bit with respect to weather system and the conditions you're in. So you can try to also predict what will the error be 2 days ahead, 4 days ahead, 6 days ahead, at any given day and not the average over many days. So then you move away from just saying what is the weather like, but also how uncertain is the weather. And for that, you can go into probabilistic forecasting, which is now we're getting closer to the topic of today. So when you look at a probabilistic forecast, then you start working with not, this is what actually happened until now, but I'm actually a little unsure when I look ahead of time what it is, but I have some indication because I know what weather patterns are coming, and I know that some of these will affect. If I'm inside a sheltered bay, then the uncertainty will be quite small on waves. But if I'm in the open sea, that weather patterns will actually affect the uncertainty quite a bit, that I don't know the weather patterns. So you can turn this into a localized uncertainty prediction. And I'm just showing here an example of how this is done in the same position. this was actually at Final 1. I didn't say that, in the German Bight, which is a kind of a super observation site. We have a lot of observations. And here you see what we call a plume plot in the gray that is now added on top of what we saw before. And you have a measurement, and you see the further you look into the future, here's actually some quite stable conditions, but then we will have uncertainty again. Now, to produce these kind of ensemble predictions, then you have to look quite, you have to do quite a lot of computations. The weather patterns are, you can say, ensemble predicted by the big global weather centers that we have providing data that you can access. But how they are downscaled still requires quite extensive computation, and it is often too expensive simply to run these ensemble downscale models. If you think of then going down towards the coast at 100-meter resolution, it becomes unfeasible, or at least not worth it. And you also have to wait longer to get the results. Now, so messages we would like to get that kind of local skill, which we don't see here. Is actually from a global model. We like to localize that with some method. So this brings me into the topic that is how to produce machine learning downscaled ensemble predictions. And it will also dwell a little bit on machine learning of mid-ocean conditions in general. Okay. Now, as I was just hinting, if you look at a local site, Then we would like to have ensemble predictions at that local site. This is a calm day, and very often it's not so nice and operative as you see here, and you'd like to know when you are there. And you'd like to minimize the production time you have to produce this and the cost of having such an ensemble prediction still at a very high quality. So you want to do it without compromising the precision. And the way you can do that, especially in areas where you have been developing assets of some types. Here we're looking at an offshore wind farm. In the design phase, you often have very good historical reproductions of some model reproductions of reality. And you can utilize that together with machine learning and the coarser predictions to achieve this goal of having ensemble predictions at local accuracy fast. And we do that by taking a data science approach. So we have all our historical data sources, and we also have observations historically when they are available. They're not needed always. And we put that together both with the physics-based models and our machine learning models and basically produce outputs. It's very schematized, this plot. I'll get to a lot more details on it. But that's, if there's one thing we should try and remember at the end of this talk, it is that we can utilize our historical knowledge, either from good models or from observations, together with how they were reproduced historically by, say, poorer models that are available in an ensemble forecast. So you can learn from the past, matching from poor to good, and you can apply that in the forecast setting to give you localized ensembles. That's kind of the main message, and that does work, as I will show later. So let's dig a little bit more into the, you can say, the model framework that we have for demonstrating this. I'm also presenting today a research project that had a certain, say, progression of logic. And it started out with us looking at we have what we call a global wave model in a fine resolution. Fine meaning that it goes up to something like 15 kilometers in some areas. Most of it is coarser. We have flexible mesh. We have 76,000 elements, and we have a quite high spectral discretization in our spectral wave model. So 36 directions and 36 frequencies. And that we have calibrated and validated against global satellite data and global in situ stations. We also have a forced with the same global meteorology coarser model that then takes only 1/20th of the time to run. So you can run 30 of these with the time of 1.5 of these and fine ones. It has 55,000 elements, 16 directions, and 25 frequencies. So of course it will give worse results. But can we, with a coarse model plus a historical learning from this to this or another data set, can we then get time down and cost down basically in looking at the ensemble, that it is good enough, but that it's almost as good? That's what we're pursuing. Just a little bit more detail on the mesh, just to show kind of a visual feeling, you can say, of how the resolution is much higher in areas with a lot of human activities. In the fine model, on the fine global wave model on the left, and the coarse global wave model on the right, which is of course much poorer result. And the difference in resolution is not because resolution is worse, it's just because the zoom is bigger. And here the resolution is 50 to 100 kilometers, and here more like 15 to 50 kilometers, 70 offshore. We're now going to, so that is part of our data set. Often when you think downscaling or if you think a real project, it is not uncommon that you are in a place where you have actually a buoy that has sat in the water for a long time, either part of in this case, part of a national network of coastal monitoring in the UK and England. For a data well directional wave rider, you have this measurement here, or it can be a project-specific measurement that you have. Of course, if you have that available, you can also use machine learning to downscale to this data directly. And for the purpose of this project, it's also really important because we want to validate without cheating, proper decomposition, etc. I'll get back to that. We also want to see how good the models are. So validation is the other purpose. In this particular case, we also have a very high resolution hindcast spectral wave model that has then been calibrated against this Blakeney overfalls data set. So when we have even higher resolution, so that's a coastal domain that looks something like this, right? When you have even higher resolution, then you have even more accurate model data, and they are then available everywhere where you have in a database those data sets sitting historically. So that's kind of the three levels. You have coarse global, you have fine global, you have a high resolution model prediction, and sometimes even better, you have an observation that is, and they can become more and more costly as you go down that ladder to achieve. So that is also a data set we have feeding into this. Now, the next part of the presentation will take us through, let's say, the progression journey of this, and I'll be stepping into detail later. But first, we'll look at the machine learning evaluation, kind of looking at global models. Then we will go into detail of how 3 of these machine learning models are performing in the downscaling. We will kind of recast what we just did in the view of what we're now developing, a machine learning framework in Python that's code-wise much more robust and easy to work with. Then we will show an example of the training of the models for an ensemble case, and then present the results. So this is what we will be showing. So machine learning evaluation here. So the goal is to improve the accuracy of the global wave model. And for this example that we put up, let's say we want to go from a course. Let's forget about ensembles for a little while. Now we have a global wave model. It's very fast. We can run it in no time. And we know it will not perform well in terms of the observations we compare to, because you cannot have a global model that's good everywhere fast. Now, we could then take features from this global wave model that is forced by global meteorology that we have for a long historical period. And we can see how can we make a machine learning? Can we kind of insert a machine learning here, or we can test a number of machine learning models that we can insert and say, can you match historically? So I know when we have winds from northeast, then I should multiply my wave model result significant wave height by 1.7, right? So because every time that happens, that appears in observations. You can ask a machine learning model to reproduce that logic, of course, much more complex with any kind of potential variation or combination of these features that you take out of your global wave model. But that, of course, requires that you have observations historically or another target data set from something that's better quality than the course. Here we have explored a number of models. So this is part of what we do. We can always, it's a good idea to start. We usually work the way and recommend to always look at simple models first, a linear regression, random forest models, polynomial regressions. We also tried, and then we're moving up in complexity to gradient booster regularization, light GBM, multi-layer perceptron, and the LSTM. So we have a number of these models we can impose, and they give different results. And the main thing, or at least our experience in mid-ocean modeling, is to do something, you can say, and often linear regression does a big part of the job. You can then make it better, but that's kind of the smaller steps then that you start improving the machine learning methods, which of course we intend to do, but having the data and learning is the main ingredient. And then we can make sure that matches the observations. So we went through all these, and because of the different properties of these models, we went into depth in terms of looking at the random forest, a gradient booster regression, and a multi-layer perceptron, and I'll be showing some results from these models in the next slide. The random forest I show first, and this is going to be a little bit the same in the three models, as I just indicated, that doing something is more important than what you exactly do. What you have on the left here, you have two rows. The top row is significant wave height, and the lower row is the mean wave period you have on the right here, you have the observed values, and on the on the right, yeah, so sorry, on the x-axis you have observed values, on the y-axis you have our coarse wave model results for this particular point of the UK East Coast, where we've compared to measurements. And you can see an overprediction, which is quite natural, considering that we use a very coarse, in this area, maybe 50-kilometer resolution to model something that is sitting at relatively not shallow. I think if maybe I forget the exact depth, but something like 20 meters, 30 meters near the coast. So there's been wave transformations that we have not modeled in our model here. Now, if you take and then you go through what I showed in the former slide, take these machine learning models, random forest, and you try to learn from history how you should correct these data set on an independent validation data set, then you get this performance on the right. So here we have again observation and on the x-axis, and we then have the machine learning prediction. So data that has seen this input, learned from an independent historical data set, how it should be transformed to match observation, and then projected, predicted, used to predict the significant wave height here. And you see a really nice match. So this method, this plot shows that both for significant wave height and wave period, we can get good predictions using quite coarse mid-ocean models that are available everywhere, plus some local information. In this case, the best possible, which was observations. And you can then reproduce a much better skill also in an independent period. I would say we would typically want to have at least 1 year of training data for doing this. If you have questions on exactly how much was used for training, you can ask, and then I'm sure Stefan will know. But we used more than a year. We used enough for this case. Then this was for random forest. Then we also went in and tested the multi-layer perceptron. This is now I will show my seniority here by saying that this used to be called ANN when I learned this way back, maybe 20 years ago, more or less. Now it's a multi-layer perceptron model, and it also performs well. You can see compared to the other one, there are small differences in how it performs. And I will say when we go on further in the presentation, this is a multi-layer perceptron, is what we are going to use in the ensemble predictions we do. It's a well-established methodology, and it has good skill here. It could have been one or the other, but we chose this one. We also looked at the gradient boosting. Again, I think there are small differences. Again, the main message of showing these different ones is that you should look into them. You should make sure that you choose the best, the one that's most suitable. But doing something is better than is more important than the detail of which method you use. Yeah. So we went through this and we could see, okay, actually it works. So kind of bottom line. It works with the skill, at least, and the accuracy I just showed in the past plots. If we want to bring this to use, okay, that could be a nice paper, and there's been papers written about it, also by many other people of similar kind of behavior. Now, if you want to use this operationally to provide a real prediction in a real system, then you also need to be able to set this up quite fast. It doesn't work that it's a 1 month setup project every time you're asked to provide an ensemble forecast at a new area. So I'm exaggerating, of course, but you need to streamline this method. So we have developed a machine learning framework that is a Python-based library following good code practice, unit test, and all these kind of things. Again, Stefan will know more about it. It's in development. It's not done yet, but we started developing that and then basically recasting. And what I just showed is kind of recasting the skill that we had in this framework. As I've explained, what we have shown is you can go from a coarse wave model to either a fine global wave model or a local, like really high resolution wave model or an observation. So that is what you have here on the left. So we have made it easy to link this up into unified data structures, etc. And we're making it easy to use data in our own services from, of course, we will be using this among others, what we call MOOD, which is DHI's Mid-Ocean on Demand data portal, where we have a lot of regionally high-resolution data sets sitting that have been optimized for areas with development, not least offshore wind application, and the DHI BlueCast service, where we know what we will have operationally. That's important when you set up to kind of define the whole problem. And we have observations. It can also be integrated either from a public or proprietary data sources, depending on what you do. So these data set we make easy accessible. That's kind of just choosing one, and then it fits, and then you take it into the machine learning framework. And inside the machine learning, it sounded, of course, quite standard. Oh, I run machine learning in like some previous plots, but there's a lot of steps to it. And you can easily, get off a tangent, or you can easily make a little mistake that is quite important. And that could, for example, come from how you do the testing, validation, data split, and other things. So we've built a number of libraries inside this machine learning framework that makes sure that these steps have good defaults, basically, because our machine learning logic, the data logic that kind of controls what is good and bad, is oftentimes the same in a mid-ocean, coastal, or offshore wind farm downscaling application. So you can actually have a good standardized set of testing and validation, a split of testing, validation, also verification data set. The feature engineering is accessible and has good defaults. It is, of course, important to have a wind if you want to downscale in the global wave height and periods, etc. Data cleaning. If it's model data, it's often fairly easy, but if it's also measurement data, you may want to maybe do some filtering of the data, take out some outliers and so forth. That's part of what you do. You need to scale the different parameters, so the machine learning optimization, the parameter tuning works best possibly, and for other reasons. You also would like the machine learning library, what I just showed, kind of a list. You'd like to choose among some models that mostly works well in mid-ocean applications. So they're easily accessible, and once you click them, it's just kind of plug and play. And when you're done, very importantly, you would like to use some of the independent observations or other data sets that you have a QA report. You understand how good did my machine learning do, and in a way that is documented and reported in a way that is expected and you can say scientifically proven and sound. So all these things is kind of in the machine learning framework that we are building now, and that we have then also used to present the results we showed earlier. Then when you have all this out of this package and you have some input data, you know what your limitations are, you go through a proper QA process so you can rely on what comes out, then that is linked to the forecasting system. Somehow that model, it can, I mean, if you sit with your own little Python script, it's simple, but if you want to integrate this into an operational system that has a lot of structure to it, to be sure that that is also a robust tool with a high uptime and can handle all kind of user requirements, then that link also has to be thought into. You can say the export of this. How do you export to something you actually have accessible, and how can you make it easy to run a new point also operationally? So that's also part of what we call the machine learning framework in this presentation. Then when you have all that, then you can link some operational data that comes in to your machine learning model, and you can spit out an ensemble model. You could also predict something that was trained by in situ data originally, like I just showed, or just a downscale model, just a single improved prediction, not without the ensemble also. There's various combinations of this when you start thinking about it, but this is basically what the machine learning framework can do. Now we get back to you can say the title of the talk, which was about ensembles, and I've kind of moved into the machine learning a little bit for a while, and now we're back to the ensembles. If you train models, machine learning models that you would like to run operationally, then if you have ensemble input, as I explained, that can from wind, then they can be used to run your global wave model ensembles that you're in control of, that you can run fast, also in forecast, and they can then. And you also can regenerate any hindcast situation you want and stuff to learn from it. Then you can put that into the machine learning model, as I just explained. Another way you could also use the best weather, like the best central prediction, which is called, in this case, we exemplified with GFS. It could also be from ECMWF or others. And again, put that through a coarse model. This could actually also be a fine model because we could afford running a single of these. You have a hindcast that you learn from, and you can then train a machine learning model specifically for a specific point that you have that somebody has requested. It could be there is a sailing race going on and we want Denmark to win the Olympics, so we could go in and downscale this from our historical data. And then this downscale model could be produced, or we could also match past observations if we'd had that for the training. And similarly for the ensembles, we could then produce a cloud of as you can say, emulated downscale high resolution models from history or an observation you have in your historical archive. So these can both be done. Yeah. Now, results fresh from the oven. So we went in, and what we will show now is one 10-day period. We're not right where we have like long-term statistics, but this is where we are. What I showed earlier when I said, oh, we also have, you can say, ensembles in our online service right now. I showed these gray lines, these gray plume plots. That is basically the same we have run here in this 10-day simulation or emulated, you can say, forecast back in 2023. So this blue line here is the quality that you would have anywhere if you run the global wave model course anywhere in the world. This, of course, exemplified for the UK East Coast. And you can see we do have an ensemble forecast, and I also show the observation here because we're now in this case the forecast is past, so we can show what actually happened afterwards, because you didn't know at the start of the time. And you can see there is a tendency for this to be biased high, as we also saw in our scatter diagram earlier. But we do have some spreading, and it's like, okay, I have a good feeling that it's going to get more uncertain if I look like day 8 or even 5, but I can't really count on the actual numbers. That's one. And the same for TO2, it's actually a bit better. So the mean period, you also have this. So, but maybe instead of running this coarse model, that would be kind of a brute force. Why don't we use the finer global wave model? Maybe that's, then we get down to 15 kilometers in this area. Maybe that's good enough. So we did that because we could do that when it's one-off without, then it's of course not so expensive. And then we ran this period again. And if you see, it probably is a bit better, but it doesn't really remove all the uncertainty. There is, there's more orange under the blue, the median line, than the slope, right? There's still a bias. It's not, I'm drawing conclusions that are not statistically, solid, but this is in the research project we're in, that that's part of the phase, right? We are exploring here. And the same down here for the period. A little more variation here in this case, a variability, but not perfect. Then in this particular area, as I said, we also had a very high resolution model. Now we have a measurement, but so far I'm pretending I don't have a measurement. So just to see how does it work if I then try to tell my global wave model and global wind datasets to try and predict what we had from our high resolution coastal model that more have a resolution of, as I recall, hundreds of meters. And that's what we see here. So all of a sudden it actually is much better. You can see we have a better distribution of orange above and below. The period of time that orange should be outside the gray area should be maybe, I think, 5%. It's from 2.5 to 97.5% percentiles we show here. So it actually is quite a bit better. So it works when you have this history. Actually, we get, I don't have to kind of excuse I can't use the total. The total starts becoming reliable for my ensemble, which is great, which is what I was looking for. And the same for, something crazy happened in my presentation mode. Sorry. This is a little weird. Okay, I will see if I can go with the mouse here. Yeah, so sorry, I'm back on track here. So we have the downscaled model, but then in this case we actually also had observation. So we could also use observation as what we trained the machine learning model to predict, because we had historical observations. And that's really this goes down. That is what we have in this final presentation, in this final plot. So this was the high resolution wave model, and this was the measurement. It does become surprisingly like little variation in this TO2 is something we're looking into, but other than that, it actually probably makes the prediction even better. But we are down to where we would need to have many of these predictions to start saying something statistically solid about it. I mean, going from here and then to the coarse, fine, high-res model, and then measurement based. It is a progression where you can easily see you improving things. Taking it the next step is future work. So that's actually the results that we wanted to show you today. And from here, you can say the future perspectives is that we would like to take this machine learning framework and finish the coding wise, like as I said, a professional scale, not researcher scale. We're going through that iteration now, that it becomes really solid and easy to use and fast to build up, such that somebody like Stefan, who knows exactly how it works, he should be able to model a new point in an hour, while somebody less trained maybe could do it in a day. So that's our development targets. Let's see if we get there. It's going to be close. So that's basically so it's easy to adapt to new positions and new data sets that are already available. Then we would also like to finalize the operational integration in BlueCast, so we can show this, that the gray curves I showed first will actually come from this. That is not the case now, but it is close. It could be done relatively fast now, but it would be a one-off case. We would like this to be more streamlined. And then, as I was already hinting, we need to look at more than a 10-day period, right? We need to look across many. We have done that for the course model validation, but it isn't perfect in many positions. So we need to start using this, a probabilistic skill score. In this case, we will work with the continuous rank probability score that both assesses, you can say, if the width of the band is correct and if the mean of it is correct. And then we will extend the uncertainty with a similar methodology to work also for wind. We have also started working on that, so that's on the shelf, but not as verified. For this case at least. And then we also are working on independent methods to predict the water level, ocean currents, where probably an ensemble prediction is less likely to give the actual uncertainty alone. That is where we're taking it, and I'm on time. So I would say thank you.